Okay, good morning. Protecting and deprotecting. When there are two steps or more than two functional groups competing or reaction with a particular reagent, all other except one should be protected after completion of reaction. Protected functional groups should be deprotected by using new reagents to get the desired products. The former process is known as the protecting and the latter is known as the deprotecting. See, for this in this example, have two functional groups. This is the ketone and ester. Ketone and ester have the similar the carbonyl functional group. That's why for the conversion of the ester into alcohol, we should protect this ketone. See, in the first step, the ketone is the protected, and then second step, uh, we uh, we hydrogenation of the ester into alcohol. Then after deprotected into previous condition of the ketone. Protection and deprotection of alcohol group by the tetrahydropyran ether, that is using tetrahydropyran. If we treat with the alcohol with tetrahydropyran in the acidic condition, we'll get tetrahydropyran ether as protected condition of the alcohol. See, this is the alcohol and tetrahydropyran ether protecting mechanism. In case of mechanism, it's simple. And this is the double bond of the tetrahydropyran, and there is the electron density higher. So electron flow towards the acid as plus, and we'll get plus charge here. And then the alcohol have the lone pair of electrons, and this lone pair of electrons attacks this plus charge and get this oxygen is the plus charge. And if we remove H plus, we'll get tetrahydropyran ether. Deprotecting in the axis of acid, we'll get again alcohol and tetrahydropyran. In case of mechanism, the tetrahydropyran ether have lone pair. This lone pair moves to the hydrogen ion, that is acid. So we'll get this product in plus in this oxygen. And if this electron of the hydrogen and carbon moves into the ring and detach from the hair, neutralizing this plus charge with this bond, and we'll get the alcohol and removal of acid. By forming benzyl ether, alcohol, when treated with the benzyl ether in the presence of tetrahydropyran or sodium hydride, we will get benzyl ether. In case of mechanism, first of all, sodium hydride is dissociated and sodium plus and hydronium ion. This hydrogen ion abstracts this hydrogen and get the hydrogen gas, and this electron is transferred toward the oxygen because this oxygen have electron density higher. So this oxygen becomes negatively charged, and this negatively charged oxygen attacks this carbon and releases this chloride, and we'll get benzyl ether. Deprotection by catalytic hydrogenation. This benzyl ether is the hydrogenated in the presence of catalyst platinum and heated, will get alcohol. By forming the methyl ether, when alcohol is treated with the methyl iodide in presence of sodium hydride, we will get methyl ether. In case of mechanism is similar is discussed above. Sodium hydride is dissociated, sodium plus and hydrogen minus. When this hydronium ion abstracts this hydrogen and get hydrogen gas, and oxygen is negatively charged, and this negative charge oxygen attacks in the carbon of the methyl and release this iodide ion, and we'll get this ether. In case of deprotecting, if we'll treat with tribromoboron and hydrolysis, we'll get alcohol. In case of mechanism, the ether have the lone pair of electron and this boron have electron deficiency because it is attached with highly electronegative 3-bromine. So this lone pair of electron transferred here in the boron and release this bromide ion. And the oxygen is the positively charged. And this bromide ion again attack on this methyl group, and this positively charged oxygen is neutralized. And again, hydrolysis will get alcohol. Formation of silyl ester protection by using the tetramethyl silyl chloride in the presence of base uh, triethylamine or sodium hydride. See, this is the tetramethyl silane. It may also uh, in the phenyl or another larger alkyl groups. So we write in general silicon chloride, whatever may, phenyl, alkyl, different kinds of alkyl. So we have taken its general, and alcohol is treated with this silyl chloride in the presence of sodium hydride and or triethylamine will get silyl ester. In case of mechanism, this hydride ion obstructs this hydrogen, and this negatively charged oxygen becomes by withdrawing this electron towards the oxygen, and negative charged oxygen attacks this silane, and chloride is removed and silyl ether is formed. The protection by using the tetrabutyl ammonium chloride flowed by the water, tetrabutyl ammonium fluoride flowed by water will get the alcohol. In case of mechanism, this fluoride ion attacks the silicon, and this electron transfer to oxygen, and negatively charged oxygen attacks on the hydrogen of water and will get product alcohol. Protection and the protection of acid, that is the carboxylic acid group, protection of acid by the formation of tetrahydropyran ester, protection by using the dihydropyran in the presence of hydride, S plus ion, S plus, that is catalyst. Carboxylic acid dihydropyran in the presence of acid will get tetrahydropyran ester. Mechanism, when this pyran is attacked by the acid, will get plus charge, and the acid have that is lone pair in this oxygen in the hydroxyl group of the carboxylic acid, and this electron attacks this plus charge, and this oxygen becomes positively charged, and the oxygen and hydrogen have electronegative difference. So the covalently bonded electrons are attracted toward the oxygen to neutralize this positive charge and remove the hydrogen ion without electrons, and we'll get ester, tetrahydropyran ester. The protection by using excess of acid will get carboxylic acid. Mechanism, when acid attacks in this oxygen of ester and positively charged becomes this oxygen, and the hydrogen is removed to neutralize this positive charge by the mechanism. First of all, this electron enters in this ring, and the bone is detached from her, neutralizing this oxygen and becomes this pyrene and the carboxylic acid. By using the formation of benzyl ester protection, the ester is treated with the potassium chloride or dimethyl formide, and benzyl chloride will get benzyl ester. Mechanism, first of all, the potassium chloride dissociate potassium plus in fluoride ion, and this fluoride ion it abstracts the hydrogen of the acid, and this negatively charged oxygen attacks in the benzyl chloride and forms the benzyl ester. Deprotection by catalytic hydrogenation of benzyl ester when in the presence of platinum and heated will get acid. Protection of silyl ester formation by treating the uh, sorry, what is one? Okay, by treating with tertiary butyl dimethylsilyl chloride or tertiary methyl silyl chloride, tertiary phenyl silyl chloride in the presence of base or triethylamine or sodium hydride. First of all, potassium fluoride is dissociated, and fluoride attacks this hydrogen and negatively charged oxygen of the acid, and it attacks benzyl chloride and forms ester. Deprotection by catalytic hydrogenation of in the presence of platinum and heated we get acid. Protection of silyl ester by treating tertiary butyl dimethylsilyl chloride and or tertiary methyl silyl chloride or tertiary phenyl chloride in presence of base. Base in the sodium hydride or triethyl ammonium. Sorry. Okay. Acid is treated with silyl chloride. It forms ester, and this hydronium ion abstract hydrogen and negatively charged oxygen of the acid, and this negatively charged attacks in the silicon of the silyl chloride and forms ester. Deprotection by using tertiary butyl ammonium fluoride. Tertiary butyl ammonium fluoride becomes will get acid from the silyl ester. In case of mechanism, this fluoride attacks the silicon, and this bond between silicon and oxygen, and the electron is abstracted to oxygen because oxygen have electrode higher electronegativity. So we'll get negative charge in this oxygen and acid H plus from water. So we'll get acid. Similarly, triethyl ammonium. This hydrogen is subtracted and negative charge attacks in silicon and forms ester, deprotection, and this acid attacks this oxygen and positively charged, and this negative part of this acid attacks the silicon and detaches from here. So we'll get acid. Formation of phenyl acyl ester protection by treating alpha haloacetophenone in the presence of base. Alpha haloacetophenone treated with acid in the presence of base will get phenyl acyl ester. In the pyridine triammonium amine or sodium hydride, the negative uh, part or lone pair of this nitrogen in case of pyridine attacks this hydrogen, and the electrons is abstracted by this oxygen due to higher electronegativity of this oxygen, and negatively charged oxygen becomes and attacks to the phenyl chloride and will get phenyl ester. The protection by using zinc in presence of acid and hydrolysis, first of all zinc and hydrochloric acid will get ester. Similarly, by the hydrogenation in presence of nickel catalyst, also we get carboxylic acid. Mechanism: the zinc have the lone valence electrons to transfer this carbon and becomes negatively charged oxygen, and as H plus from acid will get alcohol. Again, zinc transfer in an electron and becomes two electrons and towards this bond and break down from here, and we'll get acid. Formation of allyl ester protection by using the allyl chloride in the presence of base. If acid is treated with allyl chloride in the presence of base, we will get allylic ester. In case of mechanism, the base abstracts the hydrogen and negatively charged oxygen of the acid, and this negatively charged oxygen attacks on the carbon of the allyl chloride and will get allylic ester. Mechanism, the base attacks this hydrogen and negatively charged oxygen and will get allylic ester. Deprotection by using the Gilman's reagent flowing by the water. If we treat it with the Gilman's reagent, the allylic ester will get the carboxylic acid. Mechanism: the Gilman's the alkyl groups have negatively charged because the carbon have more electronegative than the metal and this copper and lithium. So this negatively charged alkyl group of Gilman's reagent attacks on this carbon because this carbon has electron deficiency. This carbon is attached to more electronegative oxygens So this electrons breakdown by abstracting by the oxygen and negative charge forms and acid hydrogen ion from the water and will get product acid. Protection and deprotection of carbonyl group by acetyl formation when treated with the carbonyl group in the alcohol, presence of acid will get acetyl. Mechanism: the ketone have this lone pair of electron is transferred to this hydrogen and will get OH plus, and when a double bond of these electrons transferred is toward this oxygen will get the positive charge on this carbon. This carbon is attacked by the alcohol and we get the positive charge in this oxygen, and this hydrogen is removed and neutralize this positive charge of the oxygen. Deprotection by using the excess of water. When excess of water, the H plus in the presence of acidic water will get this lone pair of electron of the acetyl attacks this hydrogen acid and the positive charge on this oxygen and remove as the alcohol and positive charge becomes and this carbon, and similarly again attacks this lone pair of the water and becomes uh, uh, becomes the this oxygen of water positive charge. Again this ester of the oxygen have the lone pair of electron and abstracts this hydrogen and becomes the positive charge of this oxygen. Yeah, positive charge. Consider positive charge. Remember this. Not written had positive charge, and uh, this positive charge is neutralized by this oxygen because this carbon and oxygen have the higher electronegativity in this oxygen, and this the carbon and electron, the electron between the carbon and electron is abstracted by this oxygen and neutralizes by the positive charge and removed as the alcohol and positive charge in this carbon. Again, this carbon, this oxygen and hydrogen, the covalent bond is breakdown, abstracting the lactose to this double bond and remove the H plus and we'll get ketone. Protection of the carbon, hydrogen and carbon-carbon bonds. Only highly reactive carbon-hydrogen groups, example terminal alkyls or of the carbonyl compounds have to be protected. Terminal alkyls are mostly used in organometallic synthesis and in oxidative coupling. Protection of the terminal carbon-hydrogen bond is required if another group is metallited. Without protection, rearranged organometallic compounds or polymer would be formed in uncontrollable side reaction. The most useful protecting group in this reaction is trimethylsilyl groups, which is introduced by treating with chloromethylsilane and removed by the treatment with the silver nitrate. This is protection of the alkene, tetramethylsilane chloride, and this is the deep protection when treated with the silver nitrate. Will get again alkene in case of alkene and in case of alkyne. Okay, it's all about protection and deprotection. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. That is now. Bye bye. See you again.